right, hello everyone. So since we're going to be talking to you about a format called Dwarf, we thought we'd modify the language of the presentation to match. Can you read that? Well, all right. How's that? So Sergey will be introducing the format.
So we're both from Dartmouth College. We have a lab which I would like to think of as a hacker lab. So if you're interested in education and research and hacking disguised as research, please come talk to us. We'd be very glad to hear from you. So what this is about is a really interesting discovery that we made, unexpected for us. We'll see how unexpected it will be for you. And the discovery was that all GCC compiled binaries programs, whether in C or C++, if it includes something that throws an exception, includes this dwarf bytecode these days. And what this dwarf bytecode is describing the stack frame layout for when you unwind the stack, when an exception happens. And this is something that comes packaged with every GCC compiled executable. And unbeknownst to many, there is a whole virtual machine, an interpreter, that executes this bytecode to generate its data needed to unwind the exception. And this bytecode is very powerful. It's actually Turing complete. And what it can do is it can read arbitrary process memory, of course, because it needs to unwind the stack, so it needs to read the stack, but it's not limited to the stack. It can perform other arbitrary arithmetic computations and find out where register values are saved in the stack, so that it can restore them while it walks the stack, while the exception is being processed. And so it includes the full power of arithmetic and branches in order to be able to perform these computations. And this bytecode, this language, is meant to influence the flow of the program, because this is what exception handling is. You throw, you catch, you control the flow. And finally, last but not least, it knows, being the dwarf, it knows where the gold is. It can resolve symbols. So if you're having ASLR and relying on the big bit of obscurity that it introduces, well, this bytecode, as James will show, can actually host an entire dynamic linker that will be able to resolve symbols and redirect computations to them. So, and of course, once you have a workforce like that, there is plenty of prior art that's epic. You want to take over the world, right? I'm citing some references here, the Elder Edda, the Norse epos, then of course Richard Wagner, Das Rheingold, J.R.R. Tolkien, if you remember, Rings of Power, Seven Rings for the Dwarf Lords and their halls of stone. There you go. So we're going to take over the world, exploiting the hardworking dwarf. And just a reminder as to what these things are. This is the story of the two formats, two very friendly formats, the ELF and the dwarf. ELF is the executable and linking format, and dwarf is a debugging with attributes record format. So you just wonder who came up with that name and why. ELF you expect to find in your binaries, in your object files, in your shared objects libraries, and in your core dumps. And it has many sections, as many as 30 these days in the modern executable. But we're going to look at the three very specific ones: frame header, and the GCC accept table. And if you compile a C++ program with, or a C program, into assembly, you will find a piece of gobbledygook that just doesn't belong, that is not a x86 assembly. Well, this is dwarf bytecode and the exception handling information. So we're going to show how this bytecode is actually a lot better than executable assembly. This is what it looks like in a dump. So doesn't look like executable assembly at all. This is what it looks like when loaded in a process space. So here is your typical process space. Here is a userland side of it. Here is a stack. Here are the standard libraries, which contain the full interpreter. And of course, they get loaded into every process that might throw. And this interpreter interprets the contents of EH-frame and does so by looking into EH-frame header and the GCC exception table. So basically, imagine this is your program, and it's this box. This is its virtual address space. And if you dig deeper, you find a bunch of busy dwarfs doing their thing when exception happens. And well, let's see a demo.
All right, so would you guys like to actually see this working? All right, so I have a stupid little program here. It doesn't do very much. It's kind of boring. But if I give it some input it doesn't expect, it throws an exception. So let's just take a look at the program. It's pretty innocuous. It's not calling exec. It's not doing anything fancy. Just reading standard input, writing to standard output, and throwing and catching exceptions. So I have a slightly modified version of this program. But at first glance, you shouldn't be able to tell that it's modified. So remember, if we look at the disassembly with objdump, it's not only showing us text, it's showing us init, plt, fini, ctors, dtors, so on.
Anything that looks like code, really. Anything that can be conceivably disassembled.
So here's the disassembly of the demo program I showed you. And here's the disassembly of the slightly modified one. There's no difference in their assembly. I could show you there's no difference in their data or RO data or anything either. So pretend that instead of a pointless little program, this is some daemon that does important system things. So maybe we want to run it setuid for some reason. So it should be safe, right? It looks like it's doing nothing harmful. There's no real reason to run the setuid, but pretend it's a daemon. So now we've got our demo program. So I'm not root or anything right now. I'm a normal user. So, we can say, hello, it functions as normal. It looks perfectly normal until we make it throw an exception. And now I'm root. Thank you. So let's learn how this Trojan was built.
So how is that for a rabbit out of a hat, right? This is, of course, a Trojan rabbit, a rabbit full of dwarfs, right? Well, are heavily armed, as usual.
All right, so digging deeper, down into the mines. So you might be interested in this. We have an unexplored computational model that shows up in every C++ program, or even a C program that links to a C++ library, or anything that uses the GCC exception format. Things compiled with GCJ will use something similar. All of my experiments have been with C++ so far, but the principle holds for any similar languages compiled to binary format using exceptions on the systems that use the elf and dwarf format. So this is a fresh attack vector, so it may pass unnoticed for some time. It's not something that current antivirus is going to be set up to look for. And it plays entirely within the rules. This isn't something where we're exploiting something that wasn't implemented quite right or something that someone didn't really think about. It's a computational model that was deliberately put in place for a lot of flexibility. And we think the people who designed it just didn't really think about the other possible implications. And the fact that they're hiding this computational model inside a program that you use every day that you don't think about. So at the very least, this is a fresh code hiding vector. It's hard to detect. So what this is and what it's not. So it's a new, or at least I hope new to most of you, Turing-complete computational model. Most people don't fully understand it. It's a demonstrated Trojan backdoor, as you hopefully all just saw. And as we'll get to, it's a released binary extraction and manipulation tool. It's not a one-stop memory corruption yet anyway. What I just showed you is a Trojan. And later on, I'm going to talk about some paths forward for how this might be made into an attack that you can actually make against some arbitrary process that you can feed input to, but that's not what I'm going to show today. And just, sorry, go ahead.
Yeah. So if you manage to convince the standard libraries that your EH frame is elsewhere on the stack, or whatever you manage to overwrite, the virtual machine, the interpreter, would not care where it's interpreting from.
More about that later. So just to be clear, this isn't the SEH exception overriding that you see on Windows all the time. That's been old hat for years. This is exception handling on most Unix systems. So we're working on sort of the fuzzy edge of a system. Once you're dealing with where an exception's thrown, that's a code path that isn't exercised most of the time anyway. Because most of the time when you're testing your software and testing your new features, you run through feeding it the input that it's supposed to do to work, because that's what people do most of the time. So we're already sort of in the dark corners of the program. And the logic paths aren't tested most of the time. And most people don't really know about Dwarf. I was in an interview for a government-funded research lab, and I was talking to them about my research, and I mentioned the Dwarf stuff, and one of the people in the room said, "Oh, Dwarf." And someone else said, "Oh, you actually know about that?" And he said, "No, nobody touches Dwarf." So I thought that was kind of neat.
They usually come heavily armed.
So Dwarf started as a debugging information format designed to replace stabs. For anyone who remembers stabs, it was the old format used by GDB. And it is a standard at dwarfstandard.org. They're on version 4 of the standard right now. It gives you all the source line information, variable types, stack backtraces, etc. that you use in GDB probably every week for most of you. And as a debugging format, it's responsible for the ELF sections debug info, debug line, debug frame, so on. They're all covered by the Dwarf standard. We're not interested in the debugging information. What we're interested in is that GCC, the x86 64 ABI, the Linux standards base, etc., adopted most of the Dwarf format for how to unwind the stack for use in exception handling. So there's a section EH frame instead of debug frame that holds the similar information for exception handling. So it's not identical to the Dwarf specification. There are some modifications made. There's some different version numbers used. There's some special pointer encoding, and I don't have time to go into all of that. There's sort of little nitpicky details that aren't very interesting. If you want to find out more about them, look in the Linux standards base or the x86 64 ABI. So all of the work that I've done has been on x86 64. The principles still carry over to x86 as well. 64 is a little bit more standardized.
The funny part about this is that this is in every program, but the documentation is the very devil to find.
And some of the formats I'm going to discuss aren't even standardized. Some are at the whim of GCC. Although interestingly, Clang are binary compatible. They use the exact same format from what I've seen. I haven't looked into that in detail, but it's not just GCC. Although there's no guarantee that they will not diverge. So conceptually, EH frame represents a big, huge table, which for every text address in your program tells you how to set the registers so the previous call frame can be restored in its complete information. So you see an example of what this might sort of look like. It uses the concept of a canonical frame address, which roughly corresponds to the stack pointer or the base pointer. And that's just a virtual row in the table that's used to aid in the calculation of the other rows. A lot of registers are restored by looking up a value at a certain offset from the canonical frame address. And each row can be used to calculate how to return to the previous call frame on the stack. But think about this table. It'd be huge. It'd be larger than the whole program. And we've got a lot of blank columns. We've got a lot of duplicated entries in the columns. So Dwarf and EH frame are essentially a data compression method. Bytecode necessary to generate the parts of the table that we want to see at any given time. And the bytecode is all that's required to build the table. And as you'll see, we can compute memory locations and so on as part of that bytecode. So this whole table is never built in memory. Obviously, it would be too huge. GCC, or mostly lib standard C++, calculates the parts it needs as it needs them.
So do you see how huge it is? Just imagine that this is one line per instruction, which is what it is.
EHFrame uses these structures called CIEs and FDEs. Shared information is stored in a common information entity, and for each logical block of instructions, there's a frame description entity. In simple unoptimized code, you'll generally see one FDE per function. There's no guarantee that it'll be like that. If you've got more heavily optimized code, your code blocks are split up from multiple functions in different places. There may be more than one FDE per function. For the moment, it's probably easiest to just think about one FDE per function. So you notice I've highlighted the instructions fields in the CIE and FDE. That's what we really care about.
This is where the byte code goes.
So Dwarf is really the other assembly. The Dwarf expressions are an embedded language. As Sergey mentioned earlier, there's a complete virtual machine inside libstandard C++. And this is a stack machine. For anyone who's ever used an RPN calculator, it works essentially the same way. For those of you who never have, there's a computation stack. You push values onto that stack. Arithmetic operations and so on work with the top two values or the top value. Very nice, sir. He has a RPN calculator. Computations work with the top of the stack. So we don't have any registers in this language, and we can't put things into arbitrary memory locations. No side effects. Now, GCC limits the computation stack to 64 words. This is arbitrary. There's a little comment in the GCC source code that says, this should be enough. So you may think that's not very much memory. But when was the last time you used 64 local variables? And I implemented a dynamic linker, as we'll get to, in Dwarf using less than 20 of these stack words. So 64 really should be enough for anything you need to do.
You should remember that this is the language that's specifically designed to dereference memory and compute with words and registers and values on the stack.
So this is a sample of some Dwarf instructions. I'm not going to go into all of them. If you're curious, you can read the Dwarf standard. It's the best source of information on them. So we have set location, which that tells what row of the table we're applying to. So all the instructions for a function apply through the first instruction to the last instruction of the function, unless they're overridden by a later instruction. But if we set the location to be referring to only part of a function, those instructions refer to text that occurs later in the function. So that's for moving around which row of the table we're referring to. We talked about the canonical frame address earlier, sort of roughly corresponding to the base pointer, the base of a call frame. We have an instruction that sets how the CFA is calculated from a register and an offset off of that register. And then the basic ways that registers are restored is registers are restored either from some offset from the CFA, stored on the stack, or copied from another register.
Again, think of this in the context of exception handling, frame unwinding. The CFA is sort of like the running pointer that walks the stack. The idea is that some registers have been pushed on the stack, possibly into every frame. So you need to pop them back in order to recover. And so you can actually prepare any values you want or you need or whatever caused the exception to happen.
So going back to our table, not all the columns necessarily correspond to hardware machine registers. For a given architecture, x86, x64, Spark, there's a mapping between hardware registers and the columns in the table. Dwarf just numbers them registers 1 through however many you need. So each Dwarf instruction defines the rule for one column of the table, or as we said, advances the row. And rows inherit from the rows above them within a given FDE. So we saw that most registers are restored from another register or from a location on the stack. But the Dwarf designers wanted this to be a really flexible debugging information system. Anyone could use it for any system they wanted to build. They weren't building this for some specific architecture. So they built in flexibility, a lot of flexibility. So there are two other ways to set registers. Expression and val expression. The only difference between those is that expression is dereferenced, val expression is not. In both of those instructions, set a register from the result of some expression. So expressions have their own set of instructions. And we push constant values onto the stack. We can do arithmetic, like an RPN calculator. And we can do memory dereference. And we can get the contents of a register. And we have control flow, like less than or equal to comparisons. You can skip instructions. We have a relative branch instruction. So we've got a nice Turing-complete environment here. So going back to our CIE and FDE structure, there are just a few important fields in the CIE and the FDE. The initial location and address range within the FDE just sets what text locations we're talking about in the program. The augmentation is interesting for the exception handling stuff, because this is sort of one reason that made it so easy to adapt the debugging format for exception handling. Dwarf, being flexible again, said, we'll have a special field for an augmentation string where you can define some identifier for additions you're using to the format. And so EHFrame defines a number of these. The return address is not really a register in your conventional x86 hardware. So there's a special column in the table for where control is returned to. And the CIE just sets what column in the table we're using for that.
So this is the dream of cross-platform compatibility come true, right? Now this thing brings with itself its own assembly, which is supposed to be mapped to the native architecture, and CIE does describe much of this mapping. Well, but this is the bytecode, right?
So EHFrame isn't in some nice text format. You look at this, and most of it doesn't mean much. You see the ZR and ZPLR, those are actually the augmentation strings. But the rest of it doesn't mean much. So there are existing tools that let you see what this means. This is the output from readelf. It shows you the CIE, as we talked about, with its fields. It shows you the instructions. OBJDump will do something similar. There's also a special dwarf dump tool written by David Anderson that's pretty nice, but does essentially the same thing. This doesn't let us modify anything. I should probably actually mention that David Anderson is working on a dwarf modification tool. Last time I looked at it, it wasn't very far along, but it is in the planning stages. So Katana is an ELF modification tool and shell that we developed originally for hot patching research, not related to this at all. The ELF manipulation is inspired by ELF-SH from the RSE project. Some of you are probably familiar with it. It's a pretty neat tool. And there's some possibility Katana might eventually be integrated into that tree. We're not sure yet. And Katana is not nearly as powerful as ELF-SH. For your general ELF modification needs, go to ELF-SH. Katana was built for some specialized tasks. So DwarfScript is an assembly language that I wrote, modeled after the output from dwarf dump or readelf. So Katana can spit it out, much like readelf. But Katana also has an assembler for it. So you can spit out your dwarf script, modify it as you need to, and then compile it back in, instead of poking at the individual little bytes with a hex editor. Because I tried that for a couple days, and you can write a couple little basic redirections with that, but it's not much fun, and you spend 4 hours trying to figure out one byte to modify. So this is an example of what DwarfScript looks like. This isn't a complete program, but it's similar to the readelf output, gives you the same sort of information, but we can put it back into a section.
Katana is not really a traditional dwarf weapon, but...
The project was unfortunately named before this research started, and I don't actually know the origins of the name. Sergey probably does.
A graduate student of ours started this vein of research. There is a paper about it. It will be linked from the Katana website. Generally, we love things like RSE that can treat your object space, your entire address space, as a bunch of objects and modify them and instrument them pretty much arbitrarily. There is a huge amount of flexibility there. I recommend RSE to you as just about the best way to manipulate ELF. So that was very inspiring. That inspired our hot patching research. And in the process, we came across this little dwarf hiding in there. And well,
so what can we do with this dwarf script? We can view and modify the on1 table in a human readable form. We can control the path of unwinding, how the call stacks walked. So even without the dwarf expressions, the nice Turing complete environment, we can bypass one exception handler in favor of another. That's sort of the first little gimmick I did when I was still working with a hex editor. So if the FDE has some common instructions, here we set up what register we're getting the CFA from. We see the CFA corresponds to the base pointer. And then we're restoring R16, which is the register number usually used for the return address, from an offset of 1 word from the frame address. So if we want to go to somewhere else on the call stack, if we know the space between the frames on the call stack, we just adjust the R16 rule to grab the return address from a different place on the stack. But we want to do more, and with dwarf expressions we can. We can redirect exceptions to a different handler in the program. We can find functions and resolve symbols, as I did in my demo. You saw there was no exec anywhere in that program, yet we still managed to find it. And we can calculate relocations. We can do pretty much anything. So as a basic example, suppose you have some function foo that handles the thrown exception. We want bar to handle it instead. We find out the address of bar, static analysis looking at the program. And in the FDE, we change the rules to, instead of restoring the return address from some place on the stack, we just hard code it to the place we want to jump to, if bar has a catch handler. But you probably want to do even more than this. So you can set registers, you can redirect unwinding. But how do you get off? How do you make the unwinding stop? So control of EHFrame alone isn't enough for that, because dwarf was, as a debugging format, was designed to show how you can unwind the stack frame, meant to be controlled by a debugger. It wasn't supposed to say when you should stop unwinding the stack frame, because you usually want the whole backtrace from GDB. So the x86-64 ABI doesn't cover this either, neither does the Linux standards base. This is the area where the dwarf format allows for some language-specific data and doesn't cover what the content of that should be at all. And the formats are written in such a way that exceptions from different languages using slightly different schemes can interoperate, and the details of the catch blocks, how the handlers are implemented, is language and compiler specific. So this is what lives in GCC accept table, the other section Sergey showed at the beginning. So what can we do with this section? So this section is interpreted by something called the personality routine, which lives in libgcc. It's GCC specific. As I mentioned earlier, Clang appears to use the same one. So control of it is what we need to stop the exception propagation at any point we want, even if there wasn't originally some exception handler written in that spot. But it's not governed by any standard. What I thought kind of interesting was the best documentation for this section is to read the verbose assembler emitted by GCC, because there is no documentation for it. If you look through the GCC mailing list, there are a couple instances of people asking, hey, is there any documentation for this? And Ian Lance Taylor or someone else will say, oh, it's sort of like this, but no, there isn't. So this is really the best way to find out what's going on.
So talk about weak binding of code and documentation, right? You don't even put it in the code. You generate it from the assembler. And it's sort of woven into that thing. This must be a new paradigm or something. This is really like digging deep, dwarf style, whatever. I was able to find a couple of outdated mailing list references to this sort of thing, describing how exception handling, the mechanism that's present in just about every compiled executable works. And James was able to find more. So
all right, so this is the format of the GCC accept table. It's organized into language-specific data areas, LSDAs, and there's not even any requirement that these LSDAs all have the same format, but if they're all emitted by GCC, they will. So roughly each LSDA corresponds to one block of catch handlers in your C++ program. And within the LSDA, you've got a header, a call site table, an action table, and a type table. The header is not very interesting. It's some bookkeeping information. The call site table is what determines how the handler is found. So there'd be one call site entry for each try block, because you might have multiple try blocks in a function with different handlers. And then there'll be some call sites around the try blocks to say, oh, this isn't actually part of the try block. We shouldn't handle an exception that comes through here. So the call site table then has information about what action to take if an exception is encountered within this call site. So the action table is really just a chain, a linked list of entries into the type table. The type table has C++ type info It's very language specific. We don't actually really care what the format of it is. It's just to determine whether a given block can handle an int or a string or some certain exception class.
Think of this as pattern matching on the type of the exception. This is really what it is, the runtime type matching, pattern matching in standard C++ library.
So Dwart script is capable of representing the contents of GCC accept table as well as the frame. This is possibly the first reasonably human readable representation of GCC accept table ever. So we've got a very simple program here. We have a try, we always throw, and we've got a couple catch blocks. So in Dwart script, this would look like this. I don't expect you all to absorb every detail of this at the moment. If you want a closer look at it, ask me later. But sort of each call site has a position where it begins in the text relative to the beginning of the function, and how many bytes are part of the call site, essentially how many bytes are part of the try block. And then index into the action table. The action table is a linked list, and type identifiers in the type table. So exception handling has this complex path through libgcc, libstandard C++, the user code. If the user code throws, CXA allocate exception mandated by the C++ ABI, CXA throw. CXA throw calls unwind raise exception, which is mandated by the x86-64 ABI. And essentially what that does is it unwinds one frame, it calls the personality routine, which is the language-specific handler that reads the GCC accept table contents. The personality routine says whether or not unwinding should stop. If unwinding doesn't stop, it loops and unwinds another frame, and so on. If unwinding does stop, then it actually returns into the exception handler. So it modifies the stack in such a way that when it returns, it jumps into the catch block in your function. And the catch block does some bookkeeping and runs its stuff, and execution continues.
And of course, if you control the way your information about the frames is being interpreted, you control everything on this path.
So let's see what Dwart script can do with this. We can backdoor a program that performs normally until an exception is thrown. So this is kind of nice. We've got a built-in trigger mechanism for a backdoor, and when people are giving the program the input it expects, it behaves in the way they expect it to. And the other nice thing is, if you screw up your exploit and the program crashes, well, you already entered something the program wasn't expecting, so you're already in an error state. So it's not as suspicious as it might be otherwise. So we can set up the return from an exception anywhere in the program. We have control over most of the registers, including the frame pointer. And to do this, as I showed earlier with objdump, we don't modify any of the sections that you normally think of as being executable. We've got what is essentially executable bytecode in our frame, but it's not something that we think about as being executable. It's not part of the text section.
And we do not bring in any x86 binary code, or any binary code of the target platform, whatever it might be. Because, well, of course, the friendly C++ environment brings its own assembler.
So let's take a look at how the demo works. We've got our simple C code. We can say some things to the audience. We get some input. If we get input we're not expecting, we throw. Nice, simple, innocuous code. So what we had was a return to libc attack. We built a dynamic linker, which could defeat ASLR if the library locations were randomized. And that dynamic linker was built into the Dwart code, and we found the location of the exec VPE function. And then we used the Dwart code to set up the stack in the way we wanted. So starting with where the link map begins in the user program when it's mapped into the address space. And I don't have time to go into all the details of dynamic linking. For those who aren't familiar about it, I'm happy to talk to you afterwards. But essentially, you've got a link map that's a linked list for all the libraries which are loaded into your program's address space. Each entry in the link map has information about the library base address and a pointer to a hash table, which you look up the symbol you want, and then use the symbol name to compare the chain in the bucket to make sure you've actually found the correct symbol, and in case of hash collisions. So This is the very beginning of the dwarf dynamic linker, just to give you an idea of what some of the dwarf expression operations look like, and I'll post the complete code after the talk for anyone who wants to take a look at it. The kind of neat thing is this dwarf code takes less than 200 bytes when compiled for a complete dynamic linker. And as I said, it uses fewer than 20 words on the computational stack of the 64 we have available. So once we've been able to find the symbol for execvpe, we have to find a place to jump into suitable for control. Because x86-64 uses registers for parameter passing, and we're only able to restore the registers which are callee saved, we can't jump into the beginning of a function. So this does make this particular attack somewhat dependent on the particular version of libc that you're using, because we have to find some offset into the function we want, where we'll be able to gain the control we want with registers that we are able to set. So here we've got a nice block that we're setting up things from R12, RBX, and R14, and then calling execve. And we have control over those 3 registers. So we decide, all right, we want to jump into this place. Now, I talked earlier about modifying GCC accept table to determine where execution returns to. But we can't modify the GCC accept table for libc, of course, if we're backdooring some user program. So we have to find a place that we can jump into in the user program that will then return into libc. So we insert some shell data into extra space in GCC accept table. Typically, there's a lot of extra space in GCC accept table due to the way the ELF file and memory layout are done. And this is all read by the dwarf, so if we wanted to obfuscate this, we could do that perfectly well and have the dwarf bytecode decode it. So you see we've got a shell, argument to the shell, and the name of the symbol that we're looking for.
In fact, we could probably do strong crypto, right?
Ew.
What would we use for the key?
So these are, we set up the arguments for execve in the registers we talked about, R14, R12, and RBX is R3 in the dwarf register numbering. So we have all the arguments to execve in the registers. We've located where in execvpe we want to jump into, and now we have to get there. So we can't put values directly on the stack with dwarf. But libstandard C++ is doing all these calculations, and it has these values on the stack temporarily that we're putting into registers, because it moves them from the stack into registers. So if we can figure out where on the stack we are, we essentially have a region of the stack that we have control over. So we put the stack pointer, we can control the stack pointer from dwarf. So we put the stack pointer just lower than a register holding our calculated address of execvpe. The libstandard C++ will then shove the address that we've told it to return to in the register 16 column, the return address, into the stack. And so then if we return into user code, it pops the stack. If that code then returns, it will pop the stack again, and that entry on the stack is execvpe where we want to return into. So we modify the landing pad in GCC accept table to, instead of putting us in the catch block, put us right before the return. So the stack is something like this. We're down in libstandard C++. It will pop to the user program, then it will pop to execvpe. And now we have the shell, as you saw earlier in the demo.
So this is fashionable, right, to call return-oriented. I mean, it's fashionable to call things like return to libc, return-oriented programming. Well, we were thinking of exception-oriented programming, except you see, when you're doing return-oriented programming, you need to beg for gadgets, little pieces of code. I mean, the art of doing that has been perfected in this community since 2000. We have a little write-up on the story of that, and I was privileged to give a talk at CCC about how this really went down. But the interesting thing is that most of this is irrelevant. You don't need to perform computations with borrowed instructions.
Because we have the instructions that we need in dwarf.
We bring bring your own linker, right?
So we could theoretically chain throws if we needed to, but most of the time we don't need to. Now, there are some limitations to all this cool stuff I've showed you. As I mentioned earlier, only saved registers are restored. The RDI, RSI, RDX that x86-64 uses to pass arguments to functions in simple cases, we don't have direct control over. So we can't just enter a function with arbitrary arguments. I should also mention we have limited space to work with in EH frame as we're adding in all our big, long dwarf bytecode. It is important that we be reasonably compact because we don't want to make the section any larger. It'll run into other sections, etc. However, GCC doesn't attempt to do any sort of analysis of which functions will ever actually have exception handling passing through them. So we can just look for functions that really don't need unwind information and get rid of them in our dwarf script, and that gives us a lot of extra room to do what we need. And you saw even in the pretty short program that I showed you, there was enough room to stick a dynamic linker. So in any actual interesting target, you're not likely to have much of a space problem. You just have to take a look at which functions you can get rid of the unwind information for. Also, dwarf script is difficult to debug. As I was debugging the dynamic linker, and believe me, it took a lot of debugging. I just got it working yesterday morning. I was stepping through the virtual machine in libstandard C++. So writing a debugging environment for dwarf is on my to-do list. It'd be a little nicer. And as I sort of alluded to when going over how the demo worked, there are some assumptions specific to the target system. How many bytes there are between the stack frame and various points. Jumping into a certain location within the function in libc requires us to know how many bytes into the function that is, even if we're able to calculate the library base address with the dynamic linking. So there may be some ways around some of these assumptions, ways we can calculate things, but in certain cases there are assumptions that we have to make. But there is one nice thing to think about. Dwarf can read the stack. So if we can get any sort of input on the stack from the user program, which generally isn't hard in any program that takes input of any sort, we have built-in arguments to our dwarf program. So if there are a few different versions of libc that we want to attack, we can write one exploit for them, and when we're actually triggering the backdoor, if we figure out what system we're on, we can give arguments to our dwarf script telling it which code path to take. So that's pretty cool. So the road goes on. There's future work to do. I've demonstrated a Trojan technique to you. But there may be some possibility for making this into even more. In some older versions of GCC, EHFrame and GCC accept table are actually writable at runtime in things compiled pick, so a lot of shared objects. I will mention that some versions of the JVM distributed on various systems have this writable EHFrame and GCC accept table. So they might be targets ripe for exploiting. Also, as Sergey mentioned earlier, if you control .dynamic, you can create fake program headers, libstandard C++, libgcc, read the location of the EHFrame and accept table from program headers. So if you can point it to fake information, you've got control. And there may even be some possibility for crafting malicious exceptions themselves that are thrown from code. But I have not done any research into that yet. Actually, before I get there, let me show you an example of the dwarf code that was used to, or the Katana code that was used to compile the demo. So that's an example of the Katana shell. We compile the dwarf script that we built. We load an executable ELF file. We replace the necessary sections. We write in our extra data with the bin bash string and so on, and then we save it out to an ELF file. So it's a pretty straightforward process. And that's about all. Slides and code will be available. I haven't posted them yet, but they should be up there by Monday. Unfortunately, while there are elves and dwarfs, there are no orcs. If anyone wants to make a format called orc, that would be pretty amazing. And if you want further information, really the relevant standards are the best place to look. There isn't a lot of documentation other than them in most cases.
We're going to pull together some of our reading and post it eventually, because you know, finding your way through this labyrinth of the Dwaro Delve is not an easy task. You need a wizard with you. We need to specifically again say that quite a number of people have inspired us to work in this area. The Aresi team, they're awesome. The people who looked at PAX bypass by way of invoking the dynamic linker and defeating the ASLR this way. This is frac 58, I believe, 58 or 59, bypassing PAX. This is great, and this first alerted us to how things can be done and all sorts of weird instructions that you can evoke from your payload. Locreate, look it up in uninformed, a relocator reused as a obfuscator, deobfuscator, packer, unpacker of the code. If you can craft your relocation section when your code gets loaded, it will overwrite and otherwise patch the code. It is meant to be used as something that patches up addresses. It can patch up anything. It's a finite machine, and the program comes in the shape of the relocation sections. So there are many inspirations for which we're thankful.
So I don't know if we have any time left for questions, but until I get cut off, if there are any questions. Go ahead, sir. The question was whether this works on GCC targets on Windows. I believe that it does not. However, I haven't looked into that, so that's definitely something to look into. Anything else? Yes, sir.
Were there any dwarf ninjas?
I'm sorry?
Were there any dwarf ninjas?
I am not aware of any dwarf ninjas. Sergey is a much more of a Tolkien scholar than I. However, I have never heard of the concept of a dwarf ninja.
Well, they're ninjas. You can see them, right? If you see them, they failed. Also, well, I don't know. I mean, there is a lot of discussion on the relevant mailing lists as to the military quality of dwarfs and various units of dwarfs, variously armed and arrayed. We can discuss this over beer. Generally, a dwarf, your typical dwarf is generally a dwarf is a lot more hardy and stronger than your typical human. But, you know, of course, there are some advantages that elves have over them as well.
Anything else?
Does any of this run at the time like the shared object library exploded?
No. This is all run when exception occurs. Part of the point is to make exception handling as lightweight as possible. There's absolutely no overhead incurred from it until it's necessary. Yes, sir. So that was a disassembly of all of the sections in the program which were supposed to be executable code. .text, JCR, CTORs, DTORs, init, fini, etc. And we're modifying something that isn't supposed to contain anything that's executable. So yes, if you did, you know, obviously this doesn't survive a SHA-1 sum on the program or something. If you're actually validating with a checksum that the program you have is the program you expect, then this will show something up. It is a modification to the program. Anything else? Yes, sir.
Do you happen to know if IDS commercial devices stuff?
I would be very surprised if anyone is looking at this. The question was whether any antivirus suites, I believe, are looking at this information. It is my understanding that none of them are. However, I don't have any sort of in-depth study to verify that.
Not to our knowledge. I mean, they probably should, because this is a full, think of it as a full assembly language with a full access, read access to memory, and through the caches, quite a bit of write access as well, although, of course, it's weird.
Anything else? All right, well, thank you all.